Okay. Good evening, everyone. Welcome to week 8 of problem solving session for the computational complexity course in NPTEL. My name is Bhavya. Okay. And we'll be having these classes every Tuesday, 6 p.m. So let's just begin where we left off. And that is, we were talking about circuits, various measures on circuits, sizes, depths, and so on and so forth. And we can actually and remember that each language can be said to be characterized by circuits in the following way: that when we say that a language is computed by a Turing machine, so and so, we can also say that a language is computed by a circuit family. Why family? Because for every string in the language, for every different length string in the language, you'll require an entirely different circuit for it. In other words, it's a non-uniform model, and therefore you always say a family of circuit computes that particular language. Okay. Now, since you have languages, now you can add restriction on the circuit. Example, like you are adding restrictions on the Turing machine, whether it is deterministic or whether it is time bounded or space bounded and so on. You came up with different complexity classes. Similarly, you can come up with different complexity classes here also, and one example is NC and AC classes. Okay, so NC, okay, NC, okay, is composed of NC0 union NC1 union NC2 union and so on. Okay, which is nothing but union of k is at least, or I, let's do I is at least 0 and NCI. Now, what is each NCI? So NCI, okay, is the class of languages computed by Boolean circuits over and or not, okay, over and or not, with polynomial size, okay, that is important, and depth is order log I n. Okay, example, NC0 means constant depth circuits. Language is computed by constant depth circuits. NC1 means again log depth circuits, and so on and so forth, and that is NCA. Now, what is AC? AC is again now the union of I is at least 0, AC of I. Okay. Now, what is ACI? Same thing. ACI. Okay, I'll just copy this thing. I'll just select, duplicate. Now, ACI is a class of languages computed with Boolean circuits again, polynomial size again, and depth. Okay. So both. Okay. So I'm really sorry for this. Both are depth log to the n. Problem difference is in their fan-in. What is fan-in? The number of inputs to a single gate. Okay. The fan-in here is bounded. Bounded fan-in. Okay, NC. So what does that mean? The fan-in of each gate is at most a constant. That is, it does not depend on the input size. Okay, but AC, yeah.
So I have a doubt here that while defining this NC,
Hmm.
So NC0 is having the constant depth, and
Right,
there is NC1 is having log depth, and probably NC2 would be having log square
right,
uh,
right.
depth. So, but then, I mean, the depth is gradually, decreasing, and that too by such a great amount of the log of n.
Uh,
So, yeah. So then, the most prominent one would be the depth of the NC0 only. Then why to consider NC1 or NC2?
so wait, so the depth is continuously increasing as NC to the I, right? The I increases. Constant is always smaller than log,
Oh yes, yes, I
right? And
also
log n is smaller than log n square or log
yes,
square n.
yes,
So this is, you can imagine it to slightly have more power as it increases, as the depth increases.
yes,
Okay, so yeah. Now the difference is okay. Unbounded fan-in and bounded fan-in. Unbounded means the fan-in of each gate is not upper bounded by a constant. It may even depend on n. It may even depend on it. Something like this may happen. So that way you can maybe already see which one is more powerful if you just compare AC0 and ACI and NCI. So can you say, looking at this, can you say whether and what is the relationship between NCI and ACI? So is one contained in the other? That is the question.
yes. So can you show the definitions of
Sure.
NC and AC again? Yeah. So NCI is a language computed by the Boolean circuits with the polysize and depth base, and ACI is a class of the languages with polysize and depth of
Right.
AC. So, but I could not observe the difference in between NC and then ACI.
Huh. This part is same.
Yes.
Difference is in this part. One is
Okay.
bounded fan-in, the other is unbounded fan-in. Wait, maybe the green color is not standing up.
Yes. Yes. Okay. So then, in that case, the clearly the ACI is the more powerful one than compared to the NCI.
Right, right, right. So this should mean that NCI is contained in ACI. That is the first thing we notice.
Yes.
So now what we can say. So okay. Next thing is, question is, can we compare say NCI and AC? Okay, NCI and AC. No, okay, ACI and NCI plus one. Can we compare these two?
Yes, so in case of NCI plus one, I would be having an additional circuitry of the length, say, log of I thing. But then here for the ACI, I am having unbounded
Hmm,
channel,
hmm,
and
hmm.
the NC thing I am having the bounded one.
Right,
Right. So now the question is that can I compensate
right,
more number of the inputs?
right,
Can I compensate the height with the more number of the inputs?
right, right, right.
Yes. So yeah, and for that circuitry, so indirectly the meaning is that yeah, if I increase the number of the inputs, then at the cost of including one more gate, one more AND or OR gate, because if I increase the height, I would be using an additional AND or
Right.
gate. Yeah. So
So yeah, right. So can we remove unboundedness at the cost of depth?
uh,
Right. We are allowed to give more depth, but can you remove unboundedness? That is the question. So here is a small exercise. Can you think of, like, if this is some k, can you make it? This is an OR of k. Okay, can you do OR of these? Oh, same function, but you can add more gates, but you want the fan in to be two.
Yeah, so certainly,
Hmm.
the processing carries more weight than the number of the inputs. Like, say, if I consider merely this node as an OR gate only,
Hmm.
then if I just include the number of the inputs, then eventually, if any one of them becomes one, I would only be getting one as the output. Doesn't matter that how many ones are there in the input. However, with the
Hmm.
inclusion of every element of, say, with inclusion of a gate will
Hmm.
definitely improve the processing thing. So my point is, yes, NCI plus one would be more powerful than the ECI.
Yeah. Okay. Right. I mean, the direction is correct, but can you explicitly tell how uh, this particular gate, okay, has fan in key, right?
Yes.
I want to convert it into a small circuit, okay? I want to convert it into a circuit, and you can use more gates here, but this particular circuit should have only fan in two, but it should compute the same function.
Okay. 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 So I think that
Hmm.
we have read this thing that every Boolean formula can be viewed as can be converted into three set kind of the thing or three CNF kind of the thing,
Hmm.
if not two CNFs. So uh, probably, I mean, we
Yeah,
can take.
but that is for an um, entire thing, no, entire circuit. I'm just talking about a single gate here.
Oh, I see. And the single gate is OR gate only or
Yeah, just
something?
an OR gate, one single OR gate.
Oh, I see. All right. So yes. So um, and yes. So uh, okay.
And
So
yeah,
okay. So I can do one thing that I can use many gates, many
right,
OR gates,
right,
having only two inputs,
right,
and finally I give the output as an input to the as an input to another OR gate
right,
or so that can be done.
right. You
Yes.
you do it in a tree-like fashion.
Yes. Yes. Yes.
So here's an OR gate, here's another OR gate, here's another OR gate, and so on. Okay, and so there are key inputs. So there are key leaves, right?
Yes. Yes.
Key leaves, and what is the depth? Log key,
Right.
right? This is fine into. So log key depth, key leaves. Okay, log key depth, key leaves. So every gate can be converted into a bounded Fanon set of gates. But what is happening? You are increasing the height, if you can see,
Yes.
right? You are increasing the height of the tree, the height of the circuit. So now, but now you may say something like, okay, the size of the circuit is also increasing, right?
Yes. Yes.
Size of the circuit is also increasing. One is getting converted into k many. So if there is, okay, now if there is an OR gate in that AC0 circuit, suppose C is an AC0 circuit, okay, and there is a gate G belongs to C, okay, is in circuit C, okay, and
Yes.
G is sitting here. There is a circuit and then there is a gate G and it takes several. And suppose G, okay, takes um, since it's a unbounded Fanon, it can take at most polynomial many. Since it's an AC, not AC0, sorry, ACI circuit, it can take, since the circuit itself is polynomial, the number of wires will also be polynomial at
Yes.
most,
Yes.
right? So fan in of G is at most some polynomial n to the C.
Yes.
Okay, then this guy can be converted to this using this technique, tree-like technique. This guy can be converted into another sub-circuit, another circuit, fan in of G in each of these is 2. And what is the size blow up?
So log of polynomial thing.
No, what is the size blow up? The fan in was K, and the size blow up was how many? K minus 1. No?
Yes.
Right. I mean, if there are 1, 2, 3, 4, 5, 6, yeah, if there are, the fan in was 8, suppose, then this is what we get, and the number of gates is 7. Okay. Similarly, if fan in is at most n to the C, size blow up is at most n to the C minus 1. Right.
Yes.
So now thing is, do this for entire circuit C. Okay. And you have the circuit C. What is the size blow up if not n gates, suppose poly n gates are there in C, that is the size of C is poly n, then new C prime, okay, has size at most some n to the C times poly n, which is still polynomial.
So I actually I don't remember this size blow up thing. In case if we discussed this last week.
Oh, okay, sure. I mean, what I mean is, I want to convert the entire circuit into a fan in 2 circuit.
Yes.
Okay. Now G could be G, since circuit C is an AC circuit, fan in is unbounded. It could be a function of this also. It could depend on n also. Okay, it may not be bounded by a constant. So each gate you are doing this process, and from one single gate you are getting n to the C minus 1 many gates at most. Right?
Yes. Yeah.
So now what you are doing is you are doing it for every gate G in the circuit C. Okay.
Right.
Why are you doing this? Because if you do it for every gate, then you'll get fan in 2.
Yes.
Okay. Now, but so what is the size blow up? Some order n to the C times poly n, right? For each gate. We just saw that for a single gate, for one gate, the size blow up is this. For poly n many gates, the size blow up will be poly n times order n to the C.
Right.
Now, then this is the new C prime, right? And what is the depth increase? Initially, depth was, since it's an ACI circuit, log IN, right? Now, every gate, okay, the depth is increasing by log n depth. For a, what is the depth increase here? Log C log n. Fan in was n to the C, now it became a C log n depth circuit.
Yes.
Now in any part of the circuit, originally there were at most some log IN depth, log IN gates, at most log IN gates. right?
Yes.
Now each of them you're replacing with this nice gadget here, this tree-like structure, which is of log n depth. So what is the
Mm.
new total depth? Is each of the original gates
Yes.
multiplied by the depth below up
Mm.
for each gate, which is log n, C log n, which is order log I plus 1, right? So resulting circuit is an NCI plus 1 circuit, right? So what does this mean? That any AC0, ACI language can be simulated by an NCI plus 1 circuit. So now that you have this, okay, now there are two things, okay. Now this is our conclusion number 2. Conclusion number 1 is this. If you remember, this is conclusion 1 and this is conclusion 2, then what you get is, okay, what you get is from 1 and 2, NC0 is contained in AC0 from 1 trivially, is contained in by 2 NC1, is contained in AC1, is contained in NC2, is contained in AC2, and so on and so forth.
Yes.
Right? And what is now these are also, this is an infinite chain. If you union this, let's say you include all possible circuits, okay, I mean languages here. If you union, these are still polynomial size circuits with log to the I depth. Now log to the I may be very large also. If I is great enough, then the resulting depth could be polynomial also. So this is uh, NC hierarchy is equal to AC. Okay. Now this entire union, if you do union of NCI, is equal to NC is equal to AC. Oh, okay, okay. Yeah, sure. Well, no problem. No problem. Okay. Right. So this is what we have. So this is about uh, the NC hierarchy and AC hierarchy. Okay. Now, now what we want to do is, I just a moment. I'll take reference of what I wanted to cover. Okay, that is done. Okay, okay, that is done. Okay. So now I'll move on to the last week's assignment material. So this is assignment 7. Okay. Solution. The questions are the following. How many distinct symmetric functions are there from 0, 1 to the n maps to 0, 1? Okay. So let me remind you what symmetric functions are. Let me remind you what symmetric functions are. Okay. So symmetric functions are defined as follows: f 0, 1 to the n maps to 0, 1 is said to be symmetric if for all inputs x and 0 1, it so happens that if f evaluates to 1 on an input, okay, with a certain Hamming weight, then all the inputs with the same Hamming weight will also have will evaluate to 1. Okay, so that for all x and n, f of x, okay, is equal to 1, okay, then f of y is equal to 1 for all y where size the Hamming weight, okay, let me represent it by delta. Hamming weight of y is equal to Hamming weight of x. Delta is Hamming weight, okay, Hamming weight, and delta can also be defined as the number of ones in input. Okay, so examples, if f of 1 1 0 1 1 1 1 0 1 0 is equal to 1, then all those strings which have 3 ones will also be equal to 1. Then f of 1 0 1 1 0, f of 1 1 1 0 0, f of 1 0 0 0 1 1, and so on will all evaluate to 1. Okay, so because there are the Hamming weight is same, that is Hamming weight is delta is 3 here. So this is now the question is the function is okay, so such a function is called symmetric. Okay, now the question is how many distinct symmetric functions are there from 0 1 to the n to 0 1. Now you simply do the following. Okay, instead of thinking of evaluating on each of the input, think of evaluating on strings that are having the common Hamming weight. Okay, what you do is divide inputs into different weight classes. Okay, so let's say this is the input. So these are the set of all inputs. This is 0 1 to the n. This set is 0 1 to the n. Now what you want to do is, this is weight, this is delta equals 1, delta equals 0, so there are no ones in those strings. And here is another one, this is delta equals 1. So let me give an example. Rather, I'll say that this is 0 1 to the 3 now, and here you have one possible input, and that is the only one, and delta equals 1, meaning 1 0 0 0 0 1 0 1 0, and then you have another one, delta equals 2, and here you'll have more, 1 1 0 1 0 1 0 1 1. Okay, and then delta equals 3, and so on and so on and so forth until you have delta equals n. So note the following, okay? Note the following, okay? Um, if any x, okay, if f of any x is equal to 1 for some x, then f of y is also equal to 1 for any y in same weight class as x. So even if, let's say, 110 evaluates to 1 1, f evaluates to 1 1 1 1 0, then even on 101 and 0 1 1 it will evaluate to 1 by definition of symmetric functions. And by definition of symmetric function, again, if it evaluates to 100, then if it evaluates to 1 on 100, then it will evaluate to 1 on 0 1 0 0 1 0 1 0 and so on. Okay. Now you have this setup. Okay. Now it simply means this entire guy will evaluate to a 0, or this entire guy can be thought to evaluate to 1, or this entire place can be thought to be evaluating to 0, and so on and so forth. Right? So any function, what will it do? Okay. And so it is almost like choosing. So if I say, if I color this guy red, it means I am evaluating this weight class to 0. This means I'm evaluating this weight class to 1. If I color it with green, let's say, it evaluates to 1. If I color something with, again, red, then it means it evaluates to 0. Okay, and so on. And I'm sort of coloring these two weight classes. How many possible colorings are there? Okay, that is the question. So any symmetric function, okay, f can be obtained by coloring weight classes. Let me call it C1 and so on till Cm, red or blue. Right? By coloring weight classes C1 till Cm, red or blue. That is, red means on strings in C, in weight class in Ci, f evaluates to 0. If Ci is red, Ci is green, suppose, then on strings in Ci, f evaluates to 1. So any symmetric function can be considered to be of combination of this, right? Of course, it is not exclusive that, it should only choose one weight class. It can choose several weight classes, and on those particular weight classes, it chooses to evaluate to 1 there. Okay, so that is the idea here. So I'll still give an example of a symmetric function. That is, for example, suppose say 0 0 0 0 1 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So here are the inputs. Okay, x, y, z, and a symmetric function f will look something like 0. Let's see, here it will evaluate to 1. Here it will evaluate to 1. Here it will evaluate to 0, 0, 0, 0, and here it will evaluate to 1. Look at the weight class. So this is the weight class which evaluates to green. Okay, This guy belongs to green. This also belongs to green. This guy and this guy both belong to green. And this guy belongs to green because this has having weight 1 and this has having weight 3. Okay. And the remaining, color them blue. This is colored blue. Okay. And okay, I made a mistake, sorry. This is colored green. This is colored green. This is colored green. The remaining red, red, red. So you can think of you can think of C1, C2, C2, C3, C4. Okay. Now C1, C2, C3, C4, and this guy is 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0. C3 can be thought of as 0, 1, 1, 1, 0, 1, and 1, 1, 0. And this is 1, 1. So here I'm choosing to color. This function is as if it is coloring the first color class, and the C1 as red, and C2 as green, C3 as red, and C4 as green. So this is so coloring a weight class is same as representing the symmetric function. So question is, how many ways can we color m weight classes? Well, since there are m weight classes, you can either color each you can color every weight into either of two colors, which is red and green. So 2 ways. And how many of them are there? M. So 2 into 2 into 2 into 2, so many. M many times. 2 to the m. Now what is m? How many weight classes? Well, the smallest weight class can be a weight of 0, that is this. Okay. And the largest weight can be n, so 0 to n, that is n plus 1. So, which is n plus 1, which is 0, 1, 2, and so on till n many weights possible, which is n plus 1. Okay. And so answer is 2 to the n plus 1. Okay, great. So that was the first question. Now let's look at the second question. How many distinct monotone functions are there from 0, 1, 2 bits to 1 bit? Okay, enter your answer in numeric form. So first of all, how many functions? From 2 bits to 1 bit? That is the question. So which is 0. So how many functions can you have? That is what they are asking. So 2 to the 2, answer For a Boolean function, it is 2 to the 2 to the number of bits. So it is 2 to the 2 square, which is 4, which is 16. So 16 different type of functions just on 2 bits. Okay. So for example, one function is or, another function is and. Okay. Just okay. Or and um, and XOR and so on. Okay. And this is how it goes. Now they are asking how many distinct monotone functions are there. Okay. So what is monotone now? Monotone means, okay. So you may have seen in suppose something like calculus in continuous mathematics, that what is a monotone function? It is a function that does not stop increasing. For example, this is a monotone function. Okay, and this is a monotone function, and of course this is a monotone function. But something like this is not monotone. Okay, so something like that is not monotone because it decreases down. For in the case of Boolean functions, we similarly define monotone function. Okay. In the case of Boolean function, one moment. Okay. In the case of Boolean function, when is it said to be monotone? Okay. Yeah. Now carefully look at the definition that f of x1, x2, and so on, xn, okay, equals 1, then f of y1, y2, and so on, yn is also equal to 1 for all where for all yi, for all I, yi is greater than equal to xi. I'll give an example. And is monotone. Okay, why? Because, okay, not and first. Example, okay, I'll give a simple example first. F of 0 1 0 1 1 is monotone, then flip any 0. Okay, not is monotone, equals 1. Let's say this is equal to 1 and f is monotone. Suppose monotone, this equals 1. Flip any bit, flip any 0 to 1. In other words, you are increasing the function in some sense. Okay, flip any 0 to 1. So this 0 will become 1. F of 1 1 0 1 1 is also equal to 1. Or you can flip this guy. F of 0 1 1 1 1 is also equal to. So this kind of property is that if you if on some input it evaluates to 1, then you start flipping zeros to ones, okay, and then further you flip, okay, f of 1 1 1 1 1 is also equal to 1, and it goes on like this. So this is what is called a monotone function, okay, and these are very well studied class of functions and very important too. We'll see it again later, but first they're asking how many such functions are there. An example is the AND function. Okay, AND function is monotone because 0 0 1 0 1 1 1 1 1. Okay, on 1 1 only on 1 1 it equals to 1, and there are no more zeros left to flip. So by default it is monotone. OR function is a better example because 0 0 0 1 1 0 1 1. Now on 0 1 it evaluates to 1. Flip the 0 here, you get 1 1, which for which it will always evaluate 1. Or you can see it this way also, that you have 1 0 here which evaluates to 1. Flip the 0 bit to 1 and it will always be a 1. So OR function is a nice monotone function. It's a good better example than an AND function, but both are monotone. And think of a non-trivial function. Okay. That would be something like click. Click is what is called a non-monotone function. Okay. So click. Remember that it is the set of graphs which contain a click of size k, where a click means a small complete graph. So this is monotone. Why? Because if I have my input adjacency matrix of G, okay, and this represents some graph, and there is a click here, okay, there is a click C, this is a click. Now if I flip any 0 to 1, what does it mean? We are adding edges to the graph. So I add, suppose this edge, including a 0 to 1 means I'm adding an edge to the graph. No matter where I add an edge, the click will still be there. So the function of click on a graph of size n, okay, will still evaluate to a 1, no problem. If it has a click of size k and I flip a 0 to a 1, then it will continue having the click of size k, because I'm just only adding edges, which is not removing any clicks from the graph. So click is an example of a monotone function, which is a bit non-trivial. A non-example of a monotone function, okay, a non-example of a monotone function is parity. Parity is such that x has odd number of ones. So if I take a example of a string which is in the language parity, it has odd number of ones. If I flip a 0 to a 1, it has even number of ones. If I flip another 0 to a 1, then it will have odd number of ones. Then it will evaluate to 1. Then it will evaluate to 0, and then 1 and 0 and so on. So parity is in some sense highly non-monotone. Okay. So now that we have that, so okay, how many distinct functions? Okay, so question is now how many distinct functions are there? Okay, so it's 2 bits only. So take for example xy. Okay. So 0 0 0 1 1 0 1 1, and what we can do is, one example is all are zeros. This is still monotone, but just by definition, it is still monotone. Okay, let's look at another possibility, that is the first input 0 0 evaluates to 1. Then what will happen? If I flip any one of them, they will evaluate to 1. So even if it's 0 1, I flip this 0 to 1, so it should evaluate to 1. If I flip the first bit, first 0 to a 1, then I'll get 1 0, which will evaluate to 1 by definition of monotone. And 1 1 should also be 1 by definition. So this is another example. So this is constant 0 function. This is constant 1 function. And x, y. Another possibility is that I have 0 0 0 1 1 0 1 1 here. I'll just copy this just in case. Okay. Now that I have this, I can evaluate, say, just this one to 1, and this I can do away with evaluating 0, because flipping this 0 will give a 1. So 1 0 I don't need to really. So this will be a 1. And what function is this? This is just y, in other words. So I think you can already see what another monotone function will be. And that is 0 0 0 1 1 0 1 1. Okay. And 0 0. Okay, I'll do the opposite now. On 1 0 will evaluate to 1. And here again, this will evaluate to 0, and 1 1 will evaluate to 1. It needs to evaluate to 1. It has no choice. And this is x. Okay. And let's do another one. So another choice it has is, on the first one, evaluate to 0. On both 0 1 0 and 1 and 1 0, we are evaluate to 1, and 1 1 evaluate to 1. Okay. And what function is this? This is OR. And now I think you can already guess what the next function is. Zero is okay. I have so 0 0, okay, will evaluate to a 0 0 0, and only on the last one will evaluate to 1. There's still monotone, and there's an AND function. And you can similarly check exhaustively. You will realize that only these functions out of the 16 many functions are monotone. Okay, and therefore the answer is 6. And note that unlike the symmetric case, I did not come up with a sort of general formula for this. Okay, why? Because such a general formula is not known actually, and this number of monotone functions on n bits is actually called what is called the Dedekind number. This is a mathematician who has done a lot for this theory of lattices and posets, and you'll see his name left and right in poset theory. And so this Dedekind number has a poset interpretation also. So the number of monotone functions on n bits is equal to the Dedekind number. We do not know a good approximation of Dedekind number. We do not have a good upper bound on Dedekind numbers. So we just know maybe the first few Dedekind numbers, and then the numbers get larger and larger as it goes, and then we cannot predict unless by exhaustively checking it. So this is an open problem. Okay, so monotone functions have other applications also. I'll come to that. Okay. Yeah. So we'll look at the next question. NAND is a Boolean function that returns 0 if and only if all the input bits are 1. It is a negation of the AND. So it is NAND is opposite of AND. A NAND B is nothing but negation of A and B. Okay, this is how it's defined. Now, so maybe you've seen this in digital logic. This looks like you put a round thing here, and this is a NAND gate. Okay, so you may have seen it in digital logic. If so, you know the answer already. Why? Because suppose we define new complexity class called NAND NCI to be identical to the definition of NCI, except instead of allowing OR, and NOT gates, we allow only NAND gates of n into 2. Which of the following statements is most accurate one? So if so what we are saying is, take a class just like NCI. Okay, what is NCI? Log to the I n depth. Okay, logarithmic depth, and polynomial size, okay, and bounded finite. Okay, so we are keeping everything same, except instead of and OR gates, okay, instead of and OR gates, we are talking about NAND and NAND gates. Okay, so you may have heard that NAND gates are universal. NAND gates are universal. So, and what is meant by that? Using a NAND gate, you can create any gate you want. So, using NAND gates, you can do what are called the standard basis. You can compute and or not. Okay, you can compute all of them, and if you can compute and or not, you can compute any Boolean function basically. So here's an example. And is this, you can already probably see. And what is or? Or is you can prove this using De Morgan's law. I won't prove it right now, but you can verify it if you've not seen this before. And not is obviously prove this. It's fairly simple to prove. And question is, what is the depth blow up? What is the size blow up first? So if you do this for all gates and or not gates in circuit C. Do this for all and or not gates in circuit C. Suppose you do that. Okay, suppose you do that. Then what is the size blow up? Size blow up is the worst case is when it's an OR gate and then the size increases by 3 times, right? Is at most 3 times. Right. So size of C prime is at most 3 times size of C, which is the original gate. Okay, here I write and obtain C prime. Okay, and what is the depth blow up? Is at most some constant times. Why? Because worst case is it's an AND or an OR gate. If that is the case, the gate is replaced by a sub circuit of depth 2. Instead of depth 1, it becomes a depth 2 circuit. So depth blow up is at most 2 times the depth of C. Okay. So what does it mean? NCI is contained in NAND NCI. Now by similar argument, you can do the opposite also by just placing a NAND gate. Okay. Using AND or using NAND NOT gates. Put a NOT gate in front of every gate and you can form a NAND gate, right? So you can always simulate a NAND NCI. NAND NCI. It's contained in. Okay. So these two are equal. Okay. Okay. So another question. Consider the language mult8 that consists of all n-bit integers x. Okay, which are of the form xn, xn minus 1, and so on till xn till x1 that are multiples of 8. What is the smallest value of I for which mult8 is contained in NCI? Enter your answer in numerical. So yeah, given xn x equals xn, xn minus 1, xn minus 2, so until x1. Okay, and check if x is a multiple of it. Okay, now how do you do that? So before we look at that, a simple question: how to check if x is a multiple of 2, right? How to check if x is a multiple of 2? Well, the answer is simple. Check if last bit x1, that is x1 for us, is equal to 0. Why? Why does this work out? Well, because in binary when you write it, okay, it is xn. Okay, when we write in binary in decimal, it is xn times 2 to the n minus 1 plus xn minus 1 times 2 to the n minus 2, so on and so forth, plus say x2 times 2 plus x1 times 2 to the 0. Now, if x1 survives, that is, if x1 equals 1, then since these are all powers of 2, these are all divisible by 2, right? These are all divisible by 2. All I need to do, okay, is check whether it leaves the remainder on dividing or not. So what do I do? If x1 is 1, what will happen is this 2 to 0 will leave a 1, and if x1 is 1, then I'll have a term which will be a 1 here, and this is strictly less than 2, and this will be hanging off, left off as something that I cannot divide, and this will be my remainder. Then dividing by 2 leaves a remainder 1. Now suppose I want to divide by 4. I look at this place. This place will be at most 3. I mean, if it is non-zero, okay, if either x2 or x1 is non-zero, x2 is not equal to 0 or x1 is not equal to 0, I get remainders 1, 2, 3 possible. So check for x2, x1. Similarly, for division by 8, I look at the last 3 digits. x3, check if x3 equals 0 and x2 equals 0 and x1 equals 0. If yes, output 1, otherwise 0. What will it look like? The circuit will look very simple. x3 equals 0. I can do something like x1 bar, x2 bar, x3 bar, and this will be exactly my circuit. And you have x4 and so on, xn, but these are not used. Only these 3 are used. And what is the size? Is obviously polynomial. In fact, size is 3. If you consider number of kids, okay, size is 1 if you consider the number of kids. And what is the depth? Is constant. Depth is 1, which is constant, okay, which is log to the 0. So what does it mean? It is an NC 0 circuit. Okay. So this is the answer. So here the answer is 0. Okay. Now this one is interesting. Question says, what is the value of I for which we know that log space uniform NCI is contained in L is contained in NL is contained in log space uniform NCI plus 1. Okay. Now right. Yeah. So claim is I is 1. Okay. That is NC1 is contained in L. Okay. And the second claim is that NL is contained in log space. Okay, by the way, this is log space uniform. NL is contained in log space uniform NCI plus 1. Okay. So what is meant by log space uniform? Okay. Log space uniform. I did it last time, but just to jog your memory. Log space uniform NCI means that the description of the NCI circuit can be computed in logarithmic workspace. Now, of course, since I have log space only, I cannot write the entire circuit. NCI circuit is polynomial size, so maybe I'll require polynomial space, right? So, what does mean that it can be computed? The description can be computed in log space. Since I cannot write the entire description of the circuit, I can do something like given an index I or j, okay, j, given an index j, I can tell uh, what is the jth bit in the description of the circuit. Okay, something like that I can do because I just need to write one bit, but I cannot write the entire circuit description because I'm bounded by log n space. Okay, so this is meant by log space uniform NCI. So now, how do you do it? Okay, now idea is here. Okay. Given NC1 circuit. Okay, so I have a circuit C, and this is of log depth. Now, here is the description. I want to show that it is in L. I need to construct a deterministic log space machine. Okay, description of Turing machine M. Okay, input is, suppose say x, length of x equals n. So so how do you go about doing this is with this argument I'd seen long time ago. So if there is a NAND gate, there's an OR gate below. Choose either to go left or right. Okay, first of all, what you do is now compute, okay, circuit C computing, okay, not given NCI circuit, given an L in NC, log space uniform. Okay, so this means I can compute circuit C computing L, right, on n bits. So actually, this is not what you do because, of course, like I said before, you cannot compute the entire circuit. What you need to do is whenever you want to access a particular bit in the circuit, you do the entire computation once again. Okay, the process will be very slow, but at the end it will be polynomial time only because we are running in log space. The process will be very slow. The polynomial size may be very large. Okay, but we don't care about size. We don't care about time. So now what you do is, okay, I kind of so you want to evaluate the circuit. Okay, I need to recall this. So I need to check it out once. But from what I remember, okay. from what I remember, you need to uh, do sort of a search. Okay, you go to the top gate if it is an AND. Okay, then both of these inputs need to be satisfied. Then you go through a branch. If you see an OR, then at least one of the inputs should be satisfied. And then you sort of do a left right choosing. And since it's log depth, okay. Okay, it seems I kind of forgot it, but the idea right now I'll do it next time. But I recall that okay, I read it a bit long time ago, so I recall that idea was somewhat like you just want to remember which directions you went in, okay, and for example, if you chose a 0 and in the next, so for every left you label it with a 0, for every right you label it with a 1, 0 and 1 and 0 and 1, and you sort of do this, and you go across every possible string of this sort. Okay, and what is the depth? This is log depth. So the length of the string is also log n, order log n. And then you look at the leaves, and then you sort of then do a bottom up evaluation once again, and then sort of check whether the top gate finally evaluates to 1 or not. You keep doing this process. The exact process I need to recall, but I'll come back to it. Okay, so yeah, I need to check that out. Okay, the next thing is this part 2, NL is contained in log space uniform NCI plus 1. Yeah, this is an interesting direction. Okay, so why is this interesting? Because before we were talking only about this NC AC hierarchy, right? Which was, NC is contained in AC, is contained in NC, is contained in AC, is contained with, and so on. It keeps going on. You actually break through that hierarchy and add in, these classical complexity classes. So that is, NC0 is contained in AC0, is contained in NC1, is contained in L, is contained in NL, is contained in NC2. Now, question is, why is NL contained in NC2? We already know that NL contains L. Why is NL contained in log space uniform NCI plus 1? Okay. So let's do that. Okay. I can make this uniform by, I can make this weaker by removing this, okay? But this is a stronger assumption, a stronger statement that it's contained in log space uniform. Not only that, it can be computed by such circuits, these circuits exist, but we can actually explicitly construct such circuit in log. Hmm. Now, how is this possible? Okay, this is possible because here's the claim: reachability on graphs can be solved by NCI plus 1 circuits. Okay, and to do this, I come back to an idea that we previously visited, which was about 2 weeks ago. That is what I believe it was. Okay, about 2 weeks ago, and that was using matrix multiplication to talk about reachability. Okay, we saw it in 2 instances, and one instance was in showing that BPL, okay, reachability can be done by BPL. That is, NL is contained in BPL. Okay. Okay, sure. Now let's see. Now you have this So you do a matrix multiplication. Okay. So let's look at the arithmetic matrix multiplication. Here, what do you do? Here you have A times B, okay, is equal to the first matrix A. Let's assume both are n percent, okay, just for simplicity. And you have this row multiplies with this column, okay, and the first person here multiplies with the first person there, and the first person here multiplies with second person here multiplies with second person, third person here multiplies with the third person, and so on and so forth, right? And then you add them all up, and this will form that particular. So on if this is row I and this is j, then uh, in the resulting matrix, I'll put their sum in the index ij, I comma j, that is ith row and jth column in a cross a times b. Okay. Probably cross is not a good notation. AB. In other words, AB can also be written as follows. Every index AB at ij, position ij, can be written as follows. Okay. I can write it as the sum of, okay, products. Okay, what are the products? Um, um, right. So what are the products? So for every element I in the for every uh, element in I, that is like A in the ith row for some k, okay, and in the jth row of B, jth column of B for that same k, index k. So if the first multiplies with the first part of j, the second part of I multiplies with the second part of j, and so on. So times this, and k varies from 1 to n. You can verify that this is correct. Okay, so this is the matrix multiplication formula. Okay, this is a matrix multiplication formula, and this gives that particular location in the matrix. Next, um, let's look at A times A. A times A, which is nothing but A square, or the other way around actually. A square, which is nothing but A times A, is equal to summation k equals 1 n aik times pkj. This is what you have, right? And so, and please look at the previous lecture, lecture 6, I believe. Okay. Um, I'll just quickly verify that it was lecture 6 or not. Right. The first question of lecture 6. Okay. And yeah. So look at that, and what you see is the matrix A square, okay, is talks about reachability, okay, in two steps. Okay, A square ij means can, if A is represented thought of as an adjacency matrix of a graph, then I can vertex I, okay, now this is an adjacency matrix. A is an adjacency matrix. So G, can vertex I reach vertex j in exactly two steps, two edges apart. Now similarly a to the k is can not k let's say can vertex I reach for some cell ij, for any cell ij, vertex j in exactly m steps. So this is what we have, right? And this is reachability. But this is not um, exactly reachability. Why? Because we are talking about exactly. The term here is exactly. So this is what I prefer to call reach M. Okay. All the GST such that S can reach T in graph G in M steps. Exactly. But actual reachability does not look like this, right? The original reachability does not care about what M is, does not care how many steps. GST, S can reach T. So what is happening here? Can I use this multiplication to do this? I really cannot, right? Because this is talking about reachability in M steps. I want reachability in any number of steps. So what is innately happening is when I multiply two matrices, okay, and it so happens that um, some matrix, some values get turned to 0, and then some values are 1, but when I multiply, they'll get turned to 0. Okay, you try it for yourself once. Okay, I can discuss it later also, but those locations get multiplied with 0, and you sort of forget those entries that were 1 when it reached a particular vertex in two steps. I can even give an example. Okay, I'll give a very simple example. Okay, say you have a graph G. Okay, and here I have vertex 1 goes to vertex 2, goes to vertex 3, goes to vertex 4. Okay, so this is a simple graph. So here what do we have? 1, 2, 3, 4, 1, 2, 3, 4. Now what do? I 1 is connected to 2, 2 is connected to 3, 3 is connected to 4, 4 is connected to nothing. Okay, now multiply this once. Multiply this once. What do you get? You get the first row is 0, and the second row is okay. So the first row is all zeros, and this guy is also 0. Now this is 1. Now this is 0, 0, 0, 0, 1, 0, 0, 0, 0, and then finally this all zeros. This is what you get. Now what do you get here? This is 1, 2, 1, 2, 3, 4. So 1 can reach 3 in 2 steps. 1 can reach 3 in 2 steps. 2 can reach 4 in 2 steps. And what did these mean? This means 1 can reach 2 in 1 step. 2 can reach 3 in 1 step. And 3 can reach 4 in 1 step, and so on. Right? So this is one step walk. This is a two-step walk. You sort of see that when we multiply them, the previous history is sadly gone. But we don't want that to go, because if that goes, then we cannot compute this general reachability. Right? So what we do is, here's the solution. Here's the solution. Here's the solution. Okay. Replace and with multiplication. Or what am I saying? The opposite. Multiplication with and. Replace addition with or. Okay. So my, instead of sigma of this formula, okay, so in this should be a. Okay, this formula should be, instead of summation, instead of adding, we are doing an or, and instead of multiplying, we are doing an and. Okay, and by property of and or, okay, multiplication is as almost as good as and is almost as good as multiplication, as you can see. But what is the special property of or is it that it remembers. Um, it does not remove values. Okay, let's try on the same thing. Let's try on the same thing. Same example. Same example. Let's try on the same example. Same example. Now you have this one step walk. Now what happens in the two step walk? Let's see. Can you have 1 2 3 4 1 2 3 4? Now we are doing ands of ors. Okay. So now this guy, what are we doing? We are doing ands. Ands. Okay, so ands will be 0 only here. And this row multiplied with this row is still 0, right? Now moment. Okay, when you look at 2, is there some problem here? Um, 0 1 is multiplied with this. Okay, you're somehow getting the same thing, right? 0 1 0 0 0 0. Okay, so this will be 0. This one will be 1, which will be odd with everyone else. This one will be. Okay, now I'm starting to think that is it or of hands, but it's not how I remember it was. Okay, I need to check this one too. Okay. Okay, so I'll leave this question as it is for now. Okay. So we have some unfinished business in question 12. Okay. I'll work it out properly. It seems I didn't think about it too carefully. Sorry for that. I'll come back to question 12 later on. Um, yeah, I'll fix this and in the next problem solving session. Okay. Okay. So again, more about monotone functions. Okay. Uh, okay. So you have the same question. You have the same thing. 0 1 to the n maps to 0 1 is a monotone function if for any two inputs x and y it holds that for all xy is at most yi, then f of x is at most f of y. So this is another way to define it. Okay. In other words, if you flip if x equals to 1, if you flip any of the zeros to 1, then the output will always be greater or equal. Okay. So now what we are asked to prove is prove that the composition of monotone functions is also monotone. Okay. So okay, we don't have much time. So this I'll leave it for you guys to try, but it's fairly simple. Okay. The idea is fairly simple, and just take two functions f and g. They are monotone, and okay, actually not just g. Maybe you take several functions f of f g1, g2, and so on, gk, and do f of g1, g2, and so on till gk, because these gk are single output functions, and wait, g1 of x, g2 of x, and so on till gk of x. You'll realize that okay, if f and g1 to gk are all monotone, then the composition finally will also be monotone. Okay, think of it flipping bits in the sense that if x, if you flip a bit in x, then and which is already 1, where g1 already evaluates to 1, then this will always be 1. And if f evaluates to 1 on when this bit evaluates to 1, then the entire of f will be 1. No matter how you flip the rest, and so on, since f is also monotone. So this I'll leave it for you guys to prove. So here is an interesting thing. Okay, a circuit is said to be monotone if it consists of only and OR gates. That is, no NOT gates. Remember that. Now we are asked to prove the following. For f is, okay, again 0 1 to the n maps to 0 1 is a monotone function if and only if f is computable by monotone circuits. So how do you go about proving this? Okay. First question is, what is possibly an easier direction? Okay. And this direction is actually easier. F is computable by monotone circuits. So what does mean by monotone circuits? Monotone circuits means and OR gates. Okay. And if it has only and OR gates, we already know that and OR are monotone. We said that earlier. So F is a composition of monotone functions. The actual proof can be more inductive, okay, but in otherwise F is just a several compositions of monotone functions, and therefore F is also monotone. Now let's look at the other way round. Okay. So the other way around is as follows. F is a monotone function if and only if F is computable by monotone circuits. Okay. F is monotone. Okay. So you want to make need to construct monotone circuits. Okay. Now here's a concept that will come in handy. Okay, and it's used for monotone functions, study of monotone functions, left and right, and that is the study of that is the concept of hypercubes. You may have seen it in your discrete maths course that a hypercube is like a lattice, okay, which has, so suppose a hypercube on 3 bits, something like this: 0 0 0 0 0 1 1 0 0. Now from here you have you have 0 1 1 and 1 1 0 and now here you have okay, here you have you're just doing a bitwise OR actually. So 1 0 1, okay, bitwise OR, and here you have 1 1 1. So this sort of looks like a cube if you see. So hence it's called a hypercube, or sometimes even a cube, just cube. So this is my hypercube, or also called Boolean hypercube, on 3 bits. Okay. Now any monotone function, okay, and any path from top to bottom is called a chain. Okay. For example, this is a chain. This is a chain. Okay. So now for any monotone function, okay, for any monotone function, okay, the minimum element, the minimum, which is the lowest element in a chain, in every chain, The lowest elements in every chain are called profile elements. Okay. So for example, lowest elements. Okay, in the chain um, that evaluate to 0 to 1 are called profile elements. They sort of characterize the monotone function. How? Okay, any chain actually represents flipping a 0 to 1. Flipping 0 to 1. Here it's 0 0 0. Of this blue chain, if I go, then I'm flipping this, the final bit. I'm flipping this final bit to a 1. Now, up the blue chain I go, then this second bit I'm flipping this 0 to 1. And then to 1 1 1, and so on. Similarly, green chain. First bit is flipped to a 1, then last bit is flipped to a 1, and then the middle bit is flipped. So you can see the chain actually show all possibilities of flipping bits. So what you do is actually, you go to the lowest element in that chain that evaluates to 1. Anything below that does not evaluate to 1. For example, suppose here this red element and this 110, okay, evaluates to 1. Example, profile elements are 001, okay, and 110, and do I need one more? You don't think so, right? Yeah. So okay, I think this is enough. Okay. So 00110, then then f of 00, since it's the lowest element in the chain that evaluates to 1, f of 001 is equal to everything up that chain. Everything above it evaluates to 001 and 101 and 111. Okay, and okay. Now everything above 110 is just 111. So these are all the sets for which, all the elements for which it will equal to 1. So monotone functions, okay, will always have these profile elements because each chain represents flipping a 0 to a 1. And when you flip it, the point after which, flipping 0 to a 1 starts always becoming a 1, that element is actually called the profile. So now the idea is simple. Idea, okay, and take idea is compare input with each profile element. Okay, and here is the construction. Okay, if y1, y2, and so on till yn is the profile element, then um, you want to check whether 1, okay, if the ones are actually, then for all yi's, okay, Now these are fixed. Okay, these are constants actually. Okay, these are constants. Okay, because for that particular function the profile is fixed. Then for all yi, okay, such that yi is for all yi which is equal to 1, okay, do an or of, not or, and of xi and 1, okay, and finally do or for each or across each xi and 1 term. I'll explain why. Say suppose again the profile is, suppose the profile elements are 001 and 110. Okay, I just no see the idea is that this is x1, x2, x3. Okay, okay. Now if I have anything above in this in the chain of 001, then I'm good. How do I check whether it's I'm above 001? Well, this 1 cannot be 0. This is important to me. That 1 remains as 1 because I keep 1 as it is and zeros can flip to 1. So what I do is, the for every place that is 1, that is x3, okay, I actually do an AND with a 1 so that I make sure that, oh, okay, x3 is 1. Okay, this is for the first element in the profile. For zeros, I won't do anything. I won't care because even if it is 0, if x1 and x2 are 0, and even if x1, x2 could be 1s, I don't care. They could stay the same and it will not affect my function as long as x3 is 1. Or the other way to do, other option is this: x1 is 1, okay, and x2 is 1, okay, x1 is 1 and x2 is 1, or I can even do, yeah, x1 is 1 and x2 is also 1. This is for the first element 001, and this is for the second element 110. So given something like 011, okay, input 011, this guy x3 is 1 will match, and as soon as x3 is 1 is matching, anything above the chain, for example this is above the chain, okay, since it's an OR gate, this will be valid to 1, okay, but say something like f of 011 is equal to 1, but say something like input is 111, then what will happen? X3 is 1, sorry, 000, x3 is 0, 0, so this will output 0. So nothing, so this 000 is not above in the chain of any of these two profile elements. So f of 000 is equal to 1, 0. So you keep building this. So how many profile elements could be there? Well, I mean, there could be, polynomially many, or actually exponentially many profile elements also could be possible. Nothing stopping that from happening. Okay, so but of course we are not caring about the size here. Okay, so therefore um, there exists a monotone circuit, and the circuit description is explicit and computable. That is the nice thing. The description of the circuit is explicit and computable. And yeah, and this is the construction. Okay, so there exists a monotone circuit for every monotone function. Okay, and this completes the proof. They can be seen as one and the same thing. They are sort of isomorphic, monotone functions and monotone circuits. So you can sort of see that monotone circuits are not all powerful, because obviously there are so many functions that are not monotone, right? They don't look monotone and they are not monotone, obviously. And parity is one such example, and you can come up with several such examples where they are not monotone. So it cannot be that I have a monotone circuit which computes a non-monotone function because of this particular theorem. So now you see that, okay, monotone version of circuit classes are slightly weaker than their original non-monotone classes. Okay, and similarly, you could talk about, say, something like monotone P. Okay, monotone P or monotone P slash poly, which means circuits of polynomial size, but they are monotone. Okay, what about that? Something like monotone P versus monotone NP. And something like monotone P versus monotone NC. So what are the answers here? Well, this answer is resolved. So this was resolved by KW around 91, I think. I think there's an older proof by Rasburov or something like that. But anyway, I think there's an alternate proof to this also. Yeah, but this answer is resolved. And monotone P versus monotone NP is still a question which is not answered. But and this was extensively looked forward by complexity theorists as an approach to separate P versus NP. Okay, because monotone circuit lower bounds are extremely difficult, but monotone circuit lower bounds were more hopeful. But then monotone lower bounds started coming a bit left and right, okay, compared to its non-monotone counterpart. And finally, Rasburov showed that click, okay, which is monotone, right? It is a monotone function, requires super logarithmic circuit, a super polynomial circuit. And this resolves the question. This resolves the question about monotone. And monotone as an approach to separate P versus NP may not be a good place, but it has still an important restriction. There are several conjectures and theorems, okay, which are known about their monotone counterparts, about classes, and known about monotone counterparts. And a lot of time in complexity theory, okay, which deals with sort of circuit classes and so on. And let's say there is a hard problem, which is to separate or maybe identify some circuit classes. A lot of time, to make the process slightly easier, we study the monotone variant of the problem. Okay. And first study that, and then maybe use those techniques and those tools and the experience to attack the bigger, harder problem. So, yeah. So, with that having said, okay, this is about monotone circuits. I'll close the problem solving session. Next lecture, we'll look at some more problems, but before beginning that, I'll resolve this confusion here that I had. Okay, I'm sorry for the confusion, but I'll fix this and do it first thing in the next problem session. And yeah, okay. Thank you.